Well, thank you very much for this kind invitation. It's always a pleasure to come to India, but my sincere apologies. It's a very brief visit this time. Next time I will make this up by staying for a much longer time. Touching upon the last question, it was about how sensitive can you be in exploring new physics, uncharted territories. And it was mentioned you have to take into account what other colliders have done. If we would not have electron-proton collisions in the past, I think the previous presentation would have been very, very difficult. So this is a presentation about high-energy Lepton-Hadron collisions, in general, electron-proton collisions. And I will also make a plea that what we typically know, or what we feel, what we perceive as Lepton-Hadron colliders is a QCD machine. But I will tell you as well, it's much beyond QCD as well. It is really, if you go to higher energies, a general purpose experiment. But that's the end. Ola, is this off? Okay. So we have 50 years of a great success story of DIS, deep inelastic scattering, colliding or bombarding protons or hadrons with leptons at high energies. And what is measured is typically the energy of the outgoing lepton and the angle, the scattering angle of that lepton. And we have done great things there. 50 years ago, with these kind of experiments, quarks were discovered in the proton. On another continent, a great experiment revolutionized our idea on how to look at hadrons and protons. Came along in the years after, in the decades after, was a truly partonic model of the proton. So by bombarding these protons with ever higher and higher energy electrons, we could see more and more of the internal structure of the proton. And then in the 90s of last century, came along was the precision era for deep inelastic scattering. With the Hera machine at DESY, one had electrons and protons colliding at high energies, at high luminosities as well. And from that came along were a variety of measurements of deep inelastic scattering, cross-section measurements, which then translated into parton distribution functions. That's really the legacy of the precision era of deep inelastic scattering. And what we've seen there is, for example, the rise of the gluon here at low X. And what we've seen as well is that D-glap equations, they really rule if we go and look for the substructure of protons. So that's the history. So why would you like to study this for another 50 years? That's the main aim of this presentation. Why would you like to do it also in the future? First of all, DIS is very much alive. Deep inelastic scattering organizes a big conference typically every year. And we had about 400 people registered earlier this year in May in Santiago de Compostela. Great city, great place, very dynamic research community, and lots of new innovations in the realm of deep inelastic scattering. So around the corner, and it was mentioned already before today, is a new collider that will see the light probably this decade, if not early next decade. A unique EP and E-ion scattering facility, the Electron-Ion Collider in the US, in Brookhaven. The first Electron-Ion Collider with polarized beams in the world. The user group is growing very fast, more than 1,000 people today, and growing probably to 1,500. Electrons will be shot at ions, and we'll look at the internal structures of these ions and of these protons. Looking at the phase space, the kinematic phase space of where the Electron-Ion Collider sits with respect to, for example, the Hera Collider of the 90s and the earlier part of this century is shown here. So this is the energy, center of mass energy of the collision, and this is the luminosity accumulated with these collisions. Hera was there, high energy, also high luminosity, but relative to the Electron-Ion Collider, a lower luminosity. The Electron-Ion Collider will also run at lower energies. But you see this box is much larger. This box spans a wide range in energies and also a wide range in luminosities. So a high luminosity, wide range of beam energy, polarized beams, a nuclear beam, that is, of course, a prelude for unique DIS research. So what one can do, looking at the different energies, looking at the different luminosities, there's a vast palette of research to be done at the boundaries between nuclear physics and particle physics. You see here, if you go to the upper part, so over different energy regimes, but at high luminosity, we can really make a 3D partonic image of the proton, looking what is there in the proton. And then, of course, it will be very interesting in order to go beyond longitudinal information in the proton to also take into account transversal information of partons in the proton. Having a knowledge of these transverse momenta in the proton will also feed in an improved knowledge of some of the measurements we do at the LHC. Because, of course, here you start with gluons. So it will lead to an improved understanding of the cross-section of the glue-glue to Higgs process. It will also give an improved understanding of the system, some of the systematics which we have in the measurement of the W boson mass. So clearly there is a clear, very nice collider coming alive, but it connects as well with the research we are doing at other colliders, especially in proton-proton collisions. There's a whole paper written on that in the SNOMAS process, where also there's the connection between the LHC physics and the Electron-Ion Collider physics, a real treat to read. Now towards higher energies. This was still at reasonably low energies. What happens if we go to higher energies? So if we take HERA, so from 20 years ago, we have an ambition, or we have an option, if you want, to use the proton beams at the LHC and to collide electrons with them. Or further on, in the future, we just heard about proton beams coming alive at very high energies at the FCC. We can also collide these proton beams with electrons. You see the jump made in the center of mass energy is about an order of magnitude. The jump which is realized in the peak luminosity, 10 to the 31 to 10 to the 34, is 3 orders of magnitude. Clearly, that's really a jump from the past to potentially the future. So again, on this plot of energy versus luminosity, HERA was there. The new options for the future of electron-proton collisions, they are there. Higher energies, higher luminosities. And if you translate that in the typical plane of Q squared of the interaction versus X, the fraction of energy you probe in the proton, in the orange color, that was the phase space that was coverable with the HERA collider. If you go to the blue part, this is what will be covered if you use the proton beams at the LHC with an electron beam. So clearly an extension in Q squared and clearly an extension to lower X. What does that bring? What does that bring? Well, if you have the LHEC experiment, so the experiment that would observe the electron-proton collisions at the LHC, it will run at a variety of energies. It will cover a large Q squared X range, and therefore it will get to a better knowledge of the parton distribution functions. In doing so, it will empower as well the research program of the LHC and the high luminosity LHC. It will lead to a 10 times improvement of the systematic uncertainties we have, for example, on the Higgs production cross-sections related to PDFs and the systematics due to alpha S. So that is clearly a game changer. Showing that in a plot, here you have the plot. So you have the gluon densities, the D quark, the U bar, and here the S quark, if I'm not mistaken. And you see as a function of X, the green part is where we have it with the knowledge from HERA and the LHC. If you zoom in to including the knowledge as well from the LHEC, you clearly see the phenomenal improvement. So the Higgs production would be in the range of about 0.1 in X in this case. Clearly a benefit. So clearly here as well, the DIS results you might have with the LHC would really empower, would increase the research one can do with the ATLAS and the CMS experiment. Going to even higher energies, we just heard about a potential FCC collider at 100 TeV. There as well, if you look again in X Q squared, where we have it with HERA is the orange part, and if you would have only that information on the parton distribution functions, it will translate in an uncertainty, a relative uncertainty in this case, on the production cross-section of processes with a particle X. Here is the mass of X. The green band is the uncertainty. So if I go into the electroweak range and the Higgs boson mass range, this is about 10 to the 2 GeV. And you see here in green, you have an uncertainty on the production of Z, W, and Higgs particles of about 5 to 7%. If now I bring in into the FCC program as well an electron-proton collider, you will extend your Q² X range to measure the pattern distribution functions, and that would lead to a strong reduction in the uncertainty you have on the PDFs, for example, in the Higgs, W, and Z production to the level of about 1%. And that's exactly where you would like to have it in order to do precision Higgs physics. So here as well, the FCC-EH part of the program is essential to unlock the full science potential you can have with 100 TeV proton collisions. Obviously, if we would like to make these electron-proton collisions, there is a phenomenal technological challenge, and it's related to the accelerator. Let me explain you why. Here again, the plot of the energy versus the luminosity, where we had it with Hera, where we would have it with these future electron-proton colliders. So what you see, we have about an order of magnitude in energy and 3 orders of magnitude in luminosity. That means in beam current, in the number of particles you put in the beam. The beam power can be simply calculated by multiplying the beam energy with the beam current. So 1 order, 3 orders of magnitude, the LHEC, so the electron beam, which you would have to make electron-proton collisions at the LHC, would have a beam power of 1 gigawatt. 1 gigawatt is a typical scale of what the power a nuclear power plant is producing. This is huge. This is huge. We have to deal with that. And let me explain how we deal with that. But first, let me explain where are we using this electrical power? Where and how do we use this power? And also, where do we lose the power? Very simple. This is the basic structure of a particle accelerator, or any kind of particle accelerator you can imagine. You produce the particles you would like to accelerate, you prepare the beam, you accelerate the beam. This is typically the larger structure. You do your experiment, and the rest of the beam is then typically dumped or recirculated. If you think about accelerating leptons, electrons, most of the power consumption is in the acceleration of the beam. You would like to give the power you take from the electricity grid to the beam. So there you use most of the power. So how does that work? You have your electricity grid on one side and you have your beam on the other side. You have to generate RF power because this RF power will be given to the cavities, and these cavities will give the power to the beam, to the particles in the beam. Also, you're using quite some energy in order to cool these cavities to today, typically 2 Kelvin. And there's a kind of an interplay because there's always some heat dissipation and you have to use lots of electricity in order to keep your 2 Kelvin superfluid helium at 2 Kelvin. That is costing you some power. So along the way, from the grid to the beam, you're losing in efficiency at several places. For example, the power generation from the grid to translate it into RF power, that's not fully efficient. Again, if your cavities, which work at a certain function, are somewhat detuned, well, the level of detuning squared relates again to the power needed in order to run your cavities. There's heat dissipated relating to the performance of your cavity, the famous Q0 value. And here as well, the performance of your cryogenic system. It's clear, if you want to keep a 2 Kelvin superfluid helium bath at 2 Kelvin, that's not trivial. If you dump a little bit of heat in 2 Kelvin, well, you have to use quite some power in order to keep it at 2 Kelvin. If you do exactly the same thing at 5 Kelvin, it's much easier to keep your bath at 5 Kelvin. You will produce less power. And of course, in the end, your grid energy or power is translated into beam power. And for the LHEC case, most of the grid power is indeed used to the beam power. Obviously, most of that beam power, however, is either dumped after doing the experiment or is radiated away if you have circular colliders. So you're losing quite some power there because you use the beam to circulate or in the end to dump it. So lots of R&D is being done today in order to deal with all of these aspects. For example, dealing with the RF power generation with other amplifiers, dealing with the microphonics in order to keep your cavity tuned, and also to try to invent and innovate cavities that can operate at higher temperature. And last but not least, and I will elaborate a bit on that one, of course, is how can you recover the energy of the beam after you have given the energy to the beam? It goes without saying, if we want to accelerate particles, it will always require a huge amount of energy. There is no way out. But I think there's also a challenge in there, and the challenge is unavoidable to use this energy in an optimal way. So step by step, the community at large is really gearing up for lots of R&D to what is called sustainable accelerating systems that use less energy, that need less cooling, that have less power loss, and can also recover the beam. I will not dwell on everything. I will focus here on the energy recovery part. Knowing that for these electron-proton experiments and colliders, most of the grid power is given to the beam. You would like to recover that energy from the beam before you dump it. How you do that? The principle is very simple. Again, you have your basic accelerating structures. You create the particles you would like to accelerate. You prepare the beam. You accelerate. That means you accelerate, the energies in the cavities are given to the beam. And then you do your experiment. Typically from the full beam, the experiment is only going to use a few particles, and the other billions of particles are simply continuing. So what do? You bring the same particles, the same beam back to your accelerating cavities, but your phase shift by pi, by 180 degrees. That means in the same cavities, these particles now will not be accelerated, they will be decelerated. So rather than the cavities giving energy to the beam will give energy to the cavities. Great, because that means the cavities have energy again to accelerate the next beam. The great benefit, you have recovered the energy from the beam back into the cavities, and that's almost at a level of 100%. A great thing as well, you can dump your beam at lower energies below typical activation thresholds for nuclear reactions. And maintaining the brightness of the beam from the injector is a challenge, but is also feasible because you only have one turn, or if you want multiple turns, if you want to go to higher energies. And of course, you can bring in another beam, for example, the proton beams of the LHC, and you do your experiment. Simple concept. The technology is proven. This has been done over the last several decades, but always at lower energies and at lower beam power. We have identified the key aspects in order to make this happen also at high energies and high beam power, exactly what we need for electron-proton collisions. What we need is a high current electron source. That is not trivial to produce lots of electrons, typically by shooting a laser on a cathode and then asking Einstein for advice. Of course, we would like to work further on high power SRF technology, superconductive RF structures. We would like to go to higher temperatures, not to waste money and power in cryogenic systems. As well, we would like to extract the heat load which is created in these cavities as good as possible. That is not trivial. And the fact that you have to have always beam diagnostics and instrumentation to follow your beam, in this case, you have a very dynamic range of that instrumentation, because you start with low energies and low current, and you top up and you go to higher energies. So the dynamic range of these instrumentations is critical and has to be innovated. That translated, and I will not dwell on all of this, this is maybe a slide for reference, that translated into main R&D objectives for the years to come on all of these aspects. And last but not least, also on the simulation and the education. Most of these R&D objectives, if not all, are covered, are part of two main programs in Europe. And that is the Berlin Pro and the Pearl facility. Berlin Pro, I was there by accident last week, that full accelerator is built. I will show you a picture of that. Pearl is an accelerator which is yet to come. These are two accelerator R&D programs that will come alive in Europe during this decade in order to deal with this. Where are these programs situated? Well, here I show you on the y-axis energy of the beam, and on the x-axis the average current in the cavities. And if you look at these experiments here of facilities in green, These are the previous and the current facilities operating with energy recovery mode in the world. In blue, the other side of the spectrum, if you want, you have those ERL-based particle physics colliders, for example, the LHEC, and for example, the FCC-EH. Clearly, there's a big gap. And what these lines here are exactly the power of the beam. It's energy times current, so the power is this diagonal line, and you go here from something like 1 megawatt to here 1 gigawatt. Pearl and Berlin Pro are situated in between. These are the two facilities that are the stepping stone facilities to do R&D to make happen these future ambitions in particle physics. Technology scales in that direction. Going to higher currents means innovating in technology. Going here higher in energy, if you want, is scaling, typically relates to the financial opportunities you have, making things bigger. I'm not saying there's no technological scaling there as well, but most of the technology is on this axis. If we can demonstrate that we can operate with Pearl, for example, high power ERL energy recovery Linux, then we have a clear stepping stone to make it happen as well for electron-proton collisions at the LHC or the FCC. This is a scheme of Berlin Pro. This is a facility which would fit almost in this room. So you have an injector, a particle gun if you want, you produce your particles, something called a booster. Here you have the LINAC, which is still to be built and funded, and then you have your racetrack in order to first accelerate, and then you come back, you decelerate, and you dump the beam. That's a facility which is there already in Berlin. Pearl, very similar. You create particles with a different technology in this case. You have a booster, you have a first LINAC cryo module, you do your turn, another one, and here you see you have 1, 2, 3 turns. So that is the way to go to higher energies. You have 1, 2, 3, 4, 5, 6 times accelerating, and then 6 times decelerating before you dump the beam. That would be the first demonstration of a high power energy recovery LINAC, coming alive also this decade. So with the planned R&D on energy recovery LINACs, we should be able to demonstrate energy recovery at high power beams. And that is exactly preparing the path to deal with that 1 gigawatt electron beam problem, challenge, and reducing it to 50 megawatt power. And if we can make happen that, then indeed, for the future, beyond the Electron-Ion Collider, we can have the LHEC, so electron-proton collisions at the LHC, and we can have electron-proton collisions at the FCC. Driven by remarkable technology, as I just mentioned, these technologies are not only there for particle physics, they have a vast portfolio of applications as well in industry. Coming a bit to the physics. If you go beyond HERA energies, so to the LHC and the FCC energies, your DIS experiment really becomes a general purpose experiment. Let me demonstrate that. So this is the relative, compared to HERA, on the log scale, the cross-section of EP collisions producing Higgs bosons. So clearly you see, if you go up in center of mass energy, that cross-section goes up from the LHC to the FCC. And that is really the game changer for DIS physics at high energies. It's not only a QCD machine. It is producing, through these channels, for example, a vast amount of Higgs particles, a vast amount of top particles, Ws and Zs. That is a game changer. So I will show you as well that it's not only driven by remarkable technology, but also by unique science, which is beyond QCD, also electroweak physics, Higgs physics, searches for new physics, and obviously the connection between theory and experiment is very important, like for any other collider. On one slide, I tried to capture some of the highlights of what you can do with having electron-proton collisions at the LHC, so the LHEC experiment. On Higgs physics side, so this is the precision you have on some couplings, B, W, gluon, tau, C, Z. The first bar is the precision you have in a kappa framework, precision you have which you expect to have at the end of the high luminosity LHC program, so 20 years from now. If you have as well the LHEC, you get to the I think, yellow bar. If you combine the LHC and the LHEC, you get to the dark bar. So going from the expectations of the high luminosity LHC to including as well the EP data, you have a factor of 3.5 better for the B coupling, 4 better for W, 2 for gluons, etc., etc. For the charm, probably the first time ever that this will be visible. So clearly here, you see a clear improvement with respect to the high luminosity LHC. Electroweak physics, the W mass could be measured down to 2 MeV. Today we know it at about 10 MeV. Sine squared theta Weinberg could be measured at the same level of LEP. VTB in the CKM matrix can be measured to better than 1%. Today it's known to a few percent. Obviously for DIS and for the strong interaction physics, there is a game changer, alpha S precision to the promille level. And of course, you break the frontier of low X and you go there into uncharted territories. So it's clear that the electroweak Higgs and top quark physics improvements, which you can realize with electron-proton collisions, they are very similar to the improvement factors you have between the LHC and the high luminosity LHC. So between high-lumi and the LHEC, the improvement factor is very similar to what we will realize in the next 20 years. And if you think one step further, if you would have a joint EP-PP interaction region, so one detector looking at electron-proton collisions and proton-proton collisions, that means you can correlate your measurements. I can measure the W mass here and measure the PDFs with the same experiment. You correlate the measurements, you correlate the systematics, and you open the possibility, for example, to reach a W boson mass to the 1 MeV precision, which would be phenomenal. Complementary with other colliders, and these are the last couple of slides. It was mentioned before. In the end, we have different types of colliders. Leptons colliding with each other, protons colliding with each other, leptons colliding with protons. They all bring benefit for example, exploring the Higgs sector. So what I have here is in a kappa framework, and I give you the details here, in a kappa framework, different kappa values, cross-section modifiers for a variety of colliders. And that's always, you take the high luminosity potential together with an FCC-EE potential. Or here, you take the high luminosity potential together with 100 TeV proton-proton collider. So here you see only the FCC-EE on top of the high lumi. Here you see only the FCC-HH on top of the high lumi. Let me focus on one example, the first one, and all the other lines are very similar, of course. So here you see you have a certain precision in percent. There you have a certain precision, and you can amplify that. You can really empower that. You can go better by, for example, running the FCC-EE not only at the Higgs threshold if you want, but also at the TT bar threshold. You improve a lot. You improve a lot as well by integrating the electron-proton collisions in the FCC program. And it's only by the combination of all of these types of colliders that you will reach the ultimate precision on that particular coupling with the W boson. There is a great deal of complementarity between all of these types of colliders when it comes to Higgs physics, also obviously when it comes to searches for new physics. So that is captured in the current flagship, and especially the future flagship of CERN, and I think of the rest of the world as well, where we today have the LHC. In the next 20 years, we will have the high luminosity LHC. We might have as well electron-proton collisions in that program, and thereafter we go for a Higgs factory with E plus E minus collisions, and then again, protons come into the game. This is basically a program for maybe the rest of the century. These are some references if you want. And let me end with, I tend to believe that a high energy Electron-Hadron program at the LHC and at the FCC are truly general purpose experiments. In all perception, from HERA, for example, one might think this is QCD oriented. Well, of course, it remains QCD oriented, but there's so much more you can do as really general purpose experiments for Higgs electroweak top quark physics. At the same time, these electron-proton colliders, these programs, they do empower the current research with ATLAS and CMS, and in the future with the FCC. And surely, if we go and look deeper into the proton, Basically, we have no idea what we will find there. We will break the low X frontier, and this is really terra incognita for a variety of things. And last but not least, coming to the technology point, I believe that the engine of our curiosity-driven exploration is also the way society appreciates us for the large portfolio of technological innovations that we deliver and the knowledge transfer we realize. And I tend to believe that also on this part, energy recovery systems, they do deliver on that technology front. And with that, I thank you for your attention.
Okay. Oh, there we go.
Thank you. So this is in connection with the new physics searches, especially when you are looking at, for example, the effective theory kind of a thing. Then the couplings are the ones which are going to tell us about new physics. So in that case, since we have an electron in the initial stage, I guess there are advantages that you have, for example, to look for the Lorentz structure of the couplings in addition to just how precisely you can measure it as well. Do you have a comment on it?
I don't have numbers for you at this stage,
yeah,
but of course I can give you numbers afterwards. It's obvious if you collide protons, it's much more complicated from the theoretical point of view as well. So that means it's also more complicated for the interpretation point of view of theory. If you replace a proton with an electron, you solve half of your problem. But it's still complicated, but it's true. Calculating the processes, electron-proton collisions, you can probably do that in an easier way with less systematics than proton-proton collisions. And that would also be a driver of the interpretation. That's true. I think I flashed over it. I flashed over it. Imagine on the search for new physics. Those searches for new physics are happening in a variety of ways, as you just mentioned. You can either go indirectly, see where your theory breaks, or you can look for the signal in a direct way. Recently came along where these intriguing results from, for example, LHCb, where you might have lepton flavor violation as an interpretation. Again, I'm careful in my words, you might have, etc., etc. That would mean there is something interesting going on between leptons interacting with quarks.
Yes.
What would be the best machine in order to deal with that?
Yeah, especially
I cannot give you the answer because it's a study which is much broader than this thing, but I'm sure an electron-proton collider might give you a handle, a unique handle.
Yes, I think you mentioned this top FCNC, etc. So there is a possibility, I guess. Second question is regarding this energy recovery the technology that you were telling about. Is that unique to electron beams, or is that also possible for proton? And if it is for also proton, we could, I mean, what about the Hi-Luminosity PP collider?
A very good question. Thank you for that question. It is focused on lepton beams. It is focused on lepton beams because I showed you a picture. Let me go back to the picture where I showed you where most of the power is used. I mentioned here in brackets very briefly that this was specifically for lepton accelerators. If I would make the drawing for a proton accelerator, well, the drawing is the same, but I would add here the cryogenic lines. And for the proton accelerator, most of the power is going in the cryogenic system. So that's a kind of a different thing. But positrons, obviously as well, lepton as well.
So thanks for this, painting this really wonderful picture, which is, and also particularly with the detailed discussion of energy recovery. But I wanted to ask something which was something about which you didn't talk so much, is the one machine which we're sure to have. That's EIC. So yes, there the real gain is only in luminosity, right? So I want to know what are the physics advantages over Hera, for example, that EIC would have because of the higher luminosity, even if it's lower energy.
Thank you for the question. So here I put in a spoiler alert. I have never worked at HERA and I have never worked at the Electron-Ion Collider. So here I'm going outside my comfort zone and I'm talking about research done by others, which is mostly the case. So here I gave you a sketch where luminosity is important and where energy is important on these variety of topics. It's clear with the Electron-Ion Collider, you cannot go beyond the PDFs of HERA. On the other hand, with that high luminosity, you see a different kind of structure. You can project the structure of the proton in a different way. While at HERA, it was mostly the longitudinal part. Here you will have access as well to the transverse part,
Okay.
as shown here.
Then I have a specific question with that. That here, when you spoke about polarization, is it only longitudinal polarization or is there going to be transverse polarization also? Because that is the one that would really give you that three-dimensional picture that you're talking about.
I have to check it. I have to check it.
Okay, because I
think you're right. You're right, yes, but
I mean that because that's the one that would then really help me because the transverse polarization rates are typically very small, and then the additional luminosity would help. And clearly there, I don't need the energy. I need the luminosity. So
you need the luminosity and you need the transverse polarization to some level. I have to check the exact numbers of the of that
I mean,
polarization. I don't know them by heart.
Let's thank Jorgen again.